characters. See where is. All right, here we go. All right, so we're looking at section 2.6, linear transformations. All right, so we did talk about transformations before briefly in section 2.2, right? And as I said, we will have one section where we focus on entirely transformation, and 2.6 is something we can rely on. So 2.6 talk about linear transformation. All right, so here is the precise definition of linear transformation, right? So we have transformation, but now we have linear transformation. So don't mix up with that, okay? So a transformation is considered to be linear if it satisfies the following two properties. So this is some kind of definition that we're going to use to prove and to show that whether if any transformation is a linear transformation, okay? So, when you think about function, so you have linear function, we have parabola, we have, cubic, we have square root, we have sine, cosine, all that kind of function. But then what's the characteristic of linear function? So the characteristic of linear function, it have to be a straight line, it have to have a slope, and the degree of the variable have to be 1. So same thing here in transformation. So we have a lot of transformation, but which one is a linear? So if a transformation is linear, if we can prove that it satisfies the following condition. Number one, suppose that we have all x and I in R and all scalar in R. T of x plus y must equal to t of x plus t of y. So in other words, it preserve addition. So you can do x plus y first and then apply that to the transformation, or you can do t sub x first plus t of y after. So that's the preserve of addition, and then it's also preserve a scalar multiplications, right? So you can multiply the scalar into the inputs, or you can take it out, do the transformation first, and then multiply the scalar after. So in order to prove, we can prove that it's a linear transformation if we can satisfy those two. Okay. All right. So if on the exam, when I ask you show that this is a linear transformation, then this is what you can do. You can say, well, we can prove according to the definition. Right. So here's the example that we are going to prove that this transformation is a linear transformation. All right. So the transformation we have is we go from 3-dimensional into 2-dimensional divided by when you take x1, x2, and x3 back to a 2-dimensional, then you jump out the third component. So you only have x1 and x2. All right. So now we're gonna go ahead and try to prove whether it is a linear transformation. All right. Those solutions. Right. So we need to prove t of x plus y is equal to t of x plus t sub y. That's number one. Number two, t of ax equal to a of t sub x. Right. So by definition, t of x1, x2, x3 is equal to x1, x2. Okay. So that's the definition of the formulas that we have. So when you look at this, right, so number one, so we let t of x1, x2, x3 equal to x1, x2, and t of y1, y2, y3 equal to y1 and y2, okay, by definition. So in order, if you take any transformation from three-dimensional back to two-dimensional, you just cut out the third component. So that's what we have. So t of x plus y will equal to t of x1 plus y1, x2 plus y2, x3 plus y3. Okay, by the definition of that transformation. So this one here will give us x1 plus y1 and then x2 plus y2 by the definitions of this problem. All right. So this problem says anytime that you try to transform from a three-dimensional into two-dimensional, you just cut out the third component. So if we have x1, x2, x3, you just cut out x3. If you have y1, y2, y3, you just cut out y3. And if you have x1 plus y1, x2 plus y2, and x3 plus y3, you just cut out the third component, which is x3 plus y3. Okay, so this is the left-hand side, right? And the right-hand side,
Professor, you put y2 plus y2. Just
oh, x2 right there.
Yeah.
Thank you. So the right-hand side is t sub x plus t sub y. All right. So t of x plus t sub y is equal to t of x1, x2, x3 plus with t of y1, y2, y3. So this gives us x1, x2 plus y1, y2. Okay. So this one, when you add two matrix, you will have x1 plus y1, x2 plus y2. Right. So now we can double check, right? So this is my left-hand side, right? So that's my left-hand side. The result we get is this. This is the right-hand side. The result we also get the same. So you can make that argument. So since the left-hand side equal to the right-hand side, so it's satisfied the addition condition. Does that make sense so far, guys?
Yeah. Example too.
Yeah.
All right. Yeah. So again, we just play around with the definition to see what satisfy the condition of linear or not, right? Next, what we try to do is that number two, we try to prove that t of ax equal to a t sub x, all right? So always start with the left-hand side. So left-hand side, t of ax is equivalent to t of ax1, ax2, and then ax3. Because you multiply every input by a, right? So this give us, as a transformation, will be a x1 and then a x2. And again, we jump out the third component. And then the right-hand side, a of t sub x is equal to a times t of x1, x2, x3 equal to a times with x1, x2. Now, when you distribute the a inside, you get ax1 and then ax2. Again, they are the same, right? So sin t of ax equal to a of t sub x, you can make sin the left-hand side equal to the right-hand side. That's another way to do that. Sin the left-hand side equal to the right-hand side. So it also satisfies the scalar multiplication. Therefore, t of x1, x2, x3 equal to x1, x2 is a linear transformation. So that's a picture of how we would prove something is a linear transformation. So we base solidly on the definition, right? Correct, correct, man. Yeah. So that's all we test out for. So according to the definition, so all we do is based on that definition. So, you know, just like if you want to show something is a linear function, you better show that it's have a slope, and the power of that is 1. And when you plot it, it should be a straight line. So this one same deal. So since we can really plot all the dots in the 3-dimensional, so you can see, but to be a linear transformation, it needs to satisfy those two conditions. So what we did was we tried to prove that it satisfied those two conditions, and because it satisfied those two conditions, it's enough evidence to convince us that it's a linear transformation. No problem with. Okay, are we cool with that? Yeah. Okay. All right. So you guys got down all the notes? Thumbs up if you do, so that you know to move on to the next slide. All right, good. Thank you. So later on, we will have another way to show something as a linear transformation. Okay, but for now, that's the only option that we have. Now, take a look at a few property of linear transformations. So suppose we have a transformation to be linear transformation, and x is the column vector in Rn, and since t preserves scalar multiplication, it's also preserved the zero vectors. All right. So t of 0 will be 0. So we can use this to use that as a contradiction to some transformation, whether it's a linear transformation or not. Right. So we can do that. It's also preserve a negative of a vector. So t of -1, t of negative x will be negative of t sub x, right? Because it's preserved a scalar multiplication. Therefore, we have that. All right. Now, so you can see that when you the question asks you to see whether the following are linear transformation or not, the best option is that, well, can we think of a contradiction? So in order to think of a contradiction, you can use number 1 and number 2 property to do a contradiction. So you plug in negative x to see is give you negative t sub x or not, or you can plug in t of 0 to see you get a 0 vector or not. If you don't get a 0 vector, then that's too bad. You know what I mean? All right. And then number 3, which is very important, is also preserve linear combinations. Now, what does that mean? Suppose that y is a linear combination of x1, x2, x3, and so on, then the transformation of y will also be the transformation of each of those axes. Okay, and that is very important property that we can use. All right. So transformation preserve linear transformation. All right. So make sure that you box that and put a star on that, because that's something that we are going to use quite a lot. Right. Right. So if y is a linear combination of each of those axes, then the transformation of y will also be the linear transformations of those axes. So we can take out the constant a in front and then do transformation of x1 plus a2 transformation of x2 plus dot 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 plus ak transformation of xk. That's something we can deal with. All right. Okay, so for example, right, I can have something here. Let's say t of x y equal to xy plus with 1 1. All right. So you can see here that when you do t of 0 0, you give us 0 0 plus 1 1, which equal to 1 1. And this does not equal to 0 0. You can see here it's contradict this property. Yes, it said that when you because the linear transformation preserves the 0 vector, meaning that when you plug in the 0 vector, it needs to give you the 0 vectors. But this one here, when you plug in the 0 vector, it gives you the vector 1 1. So it is not a linear transformation. Okay, so that's one counter example that you can do to show something is not a linear transformation. So that is the example. Okay. Make sense to you guys? Yeah. So if the homework asks you whether yes or no, or the question on the exam said, is the following a linear transformation? First, if you convince that I don't think it's linear transformation, then you think of the counter example. And though the first two property will be a good counter example. Yeah. All right. So the next example will take the good use of property number 3. So suppose that we have T R3 to R4 be linear transformation, right? Such that T of 1, 3, 1 give us 4, 4, 0, negative 2. T of 4, 0, 5 give us 4, 5, negative 1, and 5. So we asked to find then what is T of negative 7, 3, negative 9. All right, so there are a few important key here. We already knew that it is a linear transformation, so we don't have to verify that anymore. But now, since it's a linear transformation, then we'll be able to find the following two evaluation, right? So this one here is good. This one here also good. The question is, well, then what is T of negative 7, 3, negative 9 gonna give us? Okay, so that's what they asked. So this put us into a very awkward situation, because up there, we know the formula of the linear transformation. So the example I just threw at you a moment ago, we also know the formula of a linear transformation of the transformation. So when you evaluate, you can just use the formulas. However, this example does not provide any formulas. So how are we going to find that when we have no formulas? Well, that when property number 3 will be your best friend. Okay, because that suppose that y is a linear combination of all the x's, then the transformation of y will also be the linear transformation combination of the x's. So you can imagine that, okay, the vector 131 will be my x1, the vector 405 will be my x2, and the vector -7, 3, -9 will be my vector y. Okay, so if we can express y as a linear combination of x1 and x2, then according to property number 3, the linear combinations of the transformation of y will be the linear combination of all those x's. So that's the reason why property number 3 will be very important, so that it can help us to solve this kind of example without knowing the formula of the transformation. Okay, so that will be the plan that we're going to use. Okay. All right. So let's find what is the combination that we have, right? So we are going to use property number 3. So we are going to use property 3, which is if y is a linear combination of x1, x2, then transformation of y will be linear combination of transformations of x1 and x2. Oh, just a question. Do you guys hear any noise today or no?
It's negligible.
Okay, good. All right. So therefore we try to do that, right? So again, back to linear combinations. All right. So again, so here's the argument. So if y is a linear combination of x1, x2, then this exists AB such that y equal to ax plus ax1 plus bx2. All right. Because of that, we will have this connection -7, 3, -9 is equal to A times with 131 plus with B times with 405. All right, so remind ourselves that this guy is the vector form, yes? So we can jump into our the matrix right away, right? So therefore you have 131, 405, and then -7, 3, -9. All right, we can jump into that right away. All right. So now that's just again RIF one more time, right? So we're gonna perform RIF. We do -3 row 1 plus row 2 give you a brand new row 2, and negative row 1 plus row 3 give you a brand new row 3. So 1 4, negative 7, 0 here, so that will be negative 12, and negative 3 times negative 7, that's 21, so that will be 24, and then down here you get 0, 1, and 2. All right. Continue with that. So you get 1, 4, negative 7. So negative 1, 12, row 2, give you a new row 2. So you get 0, 12, negative 2. So here you get 0, 1, and 2. All right. So row 2 stay fixed. All right. So negative 4, row 2, plus row 1, give you a new row 1. And then negative row 2 plus row 3 give you a new row 3. So you get 1 here, you get a 0 here. So negative 4 times negative 2 is positive A plus 7 give us positive 1. And then 0, 1, negative 2. And then you have here you get 0, 0, 0. Right, so we have sin n equal to 2 and r also equal to 2. So therefore, we do n minus r, which is equal to 0. So we have one solution. Okay, we don't have infinite many solutions. We only have one solution because n is 2. We have a and b, so 2 variable, and the rank is 2. So we have one solution. All right. So what does that indicate? So therefore, so this tells us that a is equal to 1 and then b equal to minus 2. So y is equal to ax1 plus bx2 now equal to 1 times x1 minus 2 times x2. Okay, so are we good with that so far? Okay, so those are just linear combination, yeah? All right. All right, so now t sub y will equal to a t sub x1 plus with b t sub x2 by property 3. Therefore, t sub y is equal to 1 times t sub x, 1, minus 2 times t sub x2. Question, Dylan?
When you multiply row 2 by -1, wouldn't that give you -1 and positive 2? So that would 2 plus 2 is 4, not 0. Or...
Oh, initially it was 24. So you when you multiply negative 1 over 12, 24 divided negative 1 over 12 will be negative 2. Can you see that? Right here, it was 24, yes?
Wouldn't that make the
Oh, hold on. My bad.
When
1
you
second here. Yes. I think I see what you mean by that. Right. Yes. So right there, yes. 1 second here. So 20, 21 plus 4, yes. Okay, so 1 second. So negative negative row
4 instead
1.
of his...
Yep, so down here is -2. Yes, you're right. And so this one here, they're -2 here, so we get 0. Good. All right, we're still good. Yeah. Yeah, so I forgot the negative up there, right? So negative row 1 plus row 3 give us a new row 3. So negative 1 times -7 is +7 plus -9 will give us -2. Yeah. So that's where I make a mistake right there. Okay. All right. So now everything should be good. All right. Thanks for catching that, Dylan. Okay. So far, beside that, are we still good? Yeah. All right. So now t of y is equal to 1 times t of x1 and times t of x2. So for that, that's two variables, Marco, a and b. N is a number of variable. So what are we trying to solve? We try to solve for a and b, yes? We try to solve for a and b, so it will be two variable, yes. All right, so therefore, t of y, what is t of y? T of y will be -7, 3, -9, -7, 3, -9, equal to 1 times t of 1, 3, 1, minus 2 times t of 4, 0, 5. Okay, so let's small that, minimize that a little bit so you can see. Okay, so let me walk you guys through the picture again. So we don't have a formula of that transformation, therefore we cannot evaluate directly. So we have to evaluate this indirectly by going through the property number 3, which is the concept of linear combination. So if we can express y as a linear combination of x1 and x2, then the transformation of y will also be the linear combination of the transformation of x1 and x2. And that's what we did. So we have to find how do we go from -7, 3, -9 into 1, 3, 1, and then 4, 0, 5. And we did the math, and we found that, well, a will be equal to 1 and b equal to -2. So we'll be able to express oh, I'm lagging right now. Oh, must be the internet connection again. All right, so let me try to fix that. Is that better?
I think you're good now.
Okay. All right. Excuse me. All right, so now we have a linear combination. Then now we can go back and fix that, right? So now I can evaluate without a formula. I can just go indirectly through another gate, so I can get through that. All right, so by that property, now we have one. What is the transformation of 3 of 1, 3, 1? So t of 1, 3, 1 give us 4, 4, 0, -2. So 4, 4, 0, -2. And then minus with t of 4, 0, 5 give us 4, 5, -1, 5. So 4, 5, -1, and 5. Right? Because we know what is the transformation of the 2x, but we don't know what's the transformation of the y. Be able to do that, give us the transformation of the y. So here we get 4, 4, 0, -2. Minus with 8, 10, -2, and then 10. So we can conclude that t of -7, 3, -9 now equal to -4, -6, +2, and -12. So that's how we evaluate without the formulas. Okay, so that's how we evaluate without formulas. All right. Are we good on that? If you do, thumbs up, so we know to move on to the next one. All right. So now I'll go back to matrix transformations. So we know that a transformation, if it's a transformation, can be converted into a matrix times the original column vectors. Then we have ourselves a matrix transformations. All right. Now, every matrix transformation is a linear transformation. Okay, so that's a very nice thing to have, right? So every matrix transformation is a linear transformation. So meaning that if you know that is a matrix transformation, then you also know it is a linear transformation. So that's another way to prove that a transformation is a linear transformation or not, right? So how do we prove linear transformation? So we prove linear transformation by checking the two conditions. Okay. So we prove linear transformation by checking these two conditions. Now we have an alternate way to show some transformation is a linear transformation by showing that if I can show that this transformation is a matrix transformation, then it's a guarantee that it's also a linear transformation, because this theorem states that every matrix transformation is a linear transformation. All right, so that's the second way to prove whether it's a linear transformation. Okay, beside the definition. So you can prove using the definition, and you can prove using the theorem, and that's the theorem you can use if you don't want to use the definition. Okay. So again, not all transformation are matrix transformation, so we have to be very careful with that, right? So not all transformation are matrix transformation, but then every matrix transformation is a linear transformation. So that's just their special connection that we have. All right, so suppose we have here T of AB equal negative A, negative B. Is this a matrix transformation? I think we kind of go through this the other day. So we can make the argument that T of AB equal to A times with AB, right? So it said, right, if T of X equal to AX, then T of X is a matrix transformation. So T of AB is a matrix transformation. Then T of AB must equal to A times with AB. So we must show that. I think we did that before. Okay. All right. So again, start with the definitions, right? So T of AB which equal to negative A, negative B. So this can be converted into negative 1, 0, 0, negative 1, multiply with AB. Which satisfy the definitions of matrix transformation. So T of AB equal negative A, negative B is a matrix transformation. Okay, sounds good? Yeah, so that's what we did before in section 2.2, all right? So it has matrix transformation. So another example that I can ask is that is the transformation of A, B, C equal to A plus B, B plus C, A minus C, and then C minus B. A matrix transformation. Okay, so is that a matrix transformation? So if I have a transformation from ABC into A plus B, B plus C, A minus C, and then C minus B, is that a matrix transformation? So how do we figure it out whether it's a matrix transformation? So I still remember back in the day when we talk about that, right? So when you have this matrix, it's easy to think of the matrix A, because it's kind of trivial when you kind of reflect back and say, oh, I need to have a multiplication. So the next example said, well, how about A plus B, B plus C, A minus C, and C minus B? So a while ago, we did have a bit of difficulty with that example when you try to figure out, well, what is my matrix? Yeah, we did that example. So I believe it was that A equal to 1, 1, 0, 0, 1, 1, and then 1, 0, negative 1, and 0, negative 1, and 1. So that was the matrix that we were thinking of, right? So back in when we talk about section 2.2, so we did figure out that matrix, but it took us a while, all right? So the question is there an easier way to find the matrix A for that transformation, okay? So can we find the matrix A for that transformation? The answer is absolutely yes. And that easy way for us to find the matrix A depends on the definition of the standard basics of R sub n. So what is the standard basics of R sub n? So the standard basics is the set of columns E1, E2, En of I sub n, okay? So I sub n rely to the identity matrix. So the column of the identity matrix are considered to be the set of the standard basics of I sub n, okay? So the column of the identity matrix is called the standard basic of R sub n. For example, if we look at R2, okay, so R2, then we have I2, which is 1, 0, 0, 1. So that's the identity matrix. So the column, the first column, which is 1, 0, will be E1. And the second column, which is 0, 1, will be E2. So depend, excuse me, on what dimension that we have. Okay, so it doesn't have to be 2 column every single time. If you look at E3, then you have 3 columns. You have E4, then you have 4 columns. So those will be changeable also. So watch out for those definitions. All right. So here is the theorem that rely on the standard basics. It says, suppose we have a linear transformation, then T is a matrix transformation. All right. If we have a linear transformation, then it's also going to be a matrix transformation. Furthermore, T is induced by the unique matrix A, which formed by the transformation of each of those standard basics. So in other words, we can find the matrix A by evaluating T of E1, T of E2, T of E3, and so on. And we're going to form that into the column of A. So those will give us the column of A. All right, so that's a very nice thing to have. So now, up there, we know that every matrix transformation is a linear transformation. Now, this next theorem also shows us that if it is a linear transformation, then it's also a matrix transformation. So now they both work both directions. So if we know a linear transformation is a matrix transformation and vice versa, so that will be an if and only if condition. It works both directions. All right. So linear transformation imply matrix transformation and vice versa. Okay. Linear transformation imply matrix transformation, and matrix transformation imply linear transformation. Okay. So that's now they can work with each other. So you want to show something is a linear transformation, you can show that this is a matrix transformation. Therefore, it must be also linear transformation. So that's the argument we are going to make. Okay. So if you want to prove that, that's something you can use to prove. All right. So here's the example, right? Suppose that we have this linear transformation defined by T of xy equal to x plus 2y and then x minus y. So find the matrix of A. So we try to find, we know it's a linear transformation, therefore it will also be matrix transformation. So therefore we need to find what is the matrix A so that it make up a matrix transformation. All right. So by the theorems, A equal to T of E1, T of E2, right? Why am I only use T of E1 and E2? Because we're in R2, yes. So we look for I2. All right. So T of E1, which is T of 1, 0. And by definition, it will be 1 plus 2 times 0, and then 1 minus 0 by the definitions of this problem right here, okay? So that's what we are relying on. All right, so when you evaluate x and y, you get x plus 2y and then x minus y. So when I evaluate 1, 0, that I get 1 plus 2 times 0, 1 minus 0, right? So this tells me that T of E1 equal to 1, 1. And T of E2, which involves T of 0, 1. And again, by the definition same, so I get 0 plus 2 times 1 and then 0 minus 1. So we get 2 and -1. So matrix A, which equal to T of E1 and then T of E2, now can be rewritten as 1, 1, 2, -1. Now, what does that mean? It means that T of xy, which equal to x plus 2y and x minus y, can be rewritten as 1, 2, 1, -1 multiplied by xy. Well, what's the difference? The difference is this one up here is a linear transformation. This whole thing here we know as matrix transformation. Okay, is that good? Thank you, Cody. How about everyone else? Are you good with that? I see a raise of hand here. We're good to go. All right, looking good. Thank you, Anne. Thank you. Yeah, you can go ahead and take the photo of the note if you want. All right, so again, if you need me to slow down, just let me know, all right? Yeah. If you need time to write out the solutions, I say, Mr. Vo, can you slow down? I'm happy to do that. All right, so it's good to move on then. If no one have any questions, all right. All right, so you can see here, sometimes T is not defined so nicely for us. Suppose we have T of 1, 1 equal to 1, 2, and T of 0, 1 equal to 3 and 2. All right, so this one just the equal sign right there. So find the matrix A of T. All right. So this example compared to with the linear combination example that we saw before, right? So you can see here the linear combination. So they give us two transformation and they ask you to evaluate the next transformation. So we can do that linear combination easy. All right. However, in this example, they gave us two transformations, but they don't ask us to evaluate the third transformation. Instead, they said, now based on those two transformations, can you find the matrix A? Okay, so those are totally different concepts that we have, right? So if you are given by these two, can you find the matrix A? All right, that's the difference. So I don't know. There's a couple way to do this, but again, try to work with so you know there are way that work for this problem, but it doesn't work for the other problem. So we try to develop a way that works for every single problem. Okay. So the way we try to work it out here will be depend on that, on the matrix A. All right. So by the theorem, A is equal to T of E1 and then T of E2. Right. Again, we in R2, so that's what we need. Right. So by the theorem, T of E1 and T of E2. So if we can find T of E1, and we then we can be able to do that. If we can find T of E2, then we'll be able to do that. So why is that important, right? So again, we can write E1 as a linear combination of 1, 1 and 0, negative 1. Then we can find T of E1. So similarly for E2, yes? Yeah, so if we can write E1 as a linear combination of 1, 1 and 0, negative 1, then we can find the linear combination of that for sure by the property number 3, right? So you go back to property number 3, said if Y is a linear combination of x1 and x2, then we're good to go. So the transformation of x1 and x2 are provided. The only thing missing part here is your vector y. So in this case, E1, if we can do E1 as a linear combination of 1, 1 and 0, 1, then we're good to go. Okay, so that's something we can do. So this exists. AB in R such that E1 is equal to A times 1, 1 plus with B times 0, negative 1. So remind ourselves what is E1 equal. So you get A 1, 1 plot with B 0, negative 1 equal to 1, 0. And that can be converted directly into augmented matrix. So we have 1, 0, 1, 1, negative 1, and 0. All right, performing RREF, you get 1, 0, 1, and then 0, negative 1, negative 1. There we go. So A equal to 1 and then B equal negative 1. Therefore, E1 is equal to 1 times with 1, 1 minus 1 times with 0, negative 1. So T of E1 will equal to 1 times the transformation of 1, 1 minus 1 times the transformation of 0, negative 1. And this 2 we know. So transformation of 1, 1 give us 1, 2. So we get 1, 2 minus with 3, 2. And this gives us negative 2 and 0. So that would be my T of E1. All right, yes, forgot about that. Yeah, so B is equal to positive 1, yes. Mhm. There we go, positive, positive. So this become 4 and 4 and 4. All right, so A is equal to positive 1, and then B equal to positive 1 after we do that. All right, so similarly, I use different letters here. So similarly, there exists a CD in R such that E2 equal to C times 1, 1 plus with D times 0, negative 1. All right, so we get C1, 1 plus D 0, negative 1 now equal to 0, positive 1. So we can jump directly into augmented matrix 1, 1, 0, negative 1, and then 0, 1 here. So again, RREF, you get 1, 0, 0, 0, negative 1, and 1. So we get C is equal to 0, and then D equal to negative 1. Okay. So E2 equal to 0 times 1, 1 minus 1 times with 0, negative 1. Therefore, the transformation of E2 is equal to 0 times the transformation of 1, 1 minus with 1 times the transformation of 0, negative 1. So 0 times everything is 0, so we just take care of the second transformation. And the second transformation gives us 3 and 2. So we get negative 1 times with 3 and 2, which give us negative 3 and negative 2. All right, so now we have T of E1. So T of E1 equal to 4 and 4. And then T of E2 is equal to negative 3 and negative 2. All right, so since you can make the argument, since A is equal to T of E1 and then T of E2, therefore A can equal to 4, 4 and negative 3, negative 2. All right, so that is how we are using the concept of linear combinations and the matrix transformation to find the matrix A when we don't know the formulas. Yeah. So if we know the formulas, very easy. You just plug in E1 and E2 and evaluate, get the answer done. Now, if you don't have the formula, then we have to go indirectly to get the matrix A. So we still, play around with the theorem that A always equal to T of E1, T of E2, T of E3, and so on. So in this case, since we don't have the formula, we have to play around with the linear combination of E1 and E2. And that's the reason why we go ahead and find how can we combine the given input together with the standard basics of R2, of N2, I2. And then same thing with E2. So if we be able to find both E1 and E2 transformation of that, then we can be able to find the matrix A. So there's another way that I tried, but it does give us the answer for this example. But I haven't tried out with any other problem yet, so therefore I don't know whether it's capable for us to try. So what I did was is that just another approach. You can find that's better. So we define, right? We define t of xy is equal to a times xy. Okay. So that's what we define. Okay. So we let a equal to a, b, c, d, because this one is the matrix 2 by 2 matrix, right? So that's what we have. So t of what is that? T of 1 1 equal to 1 2. So t of 1 1 equal to a, b, c, d times with 1 1, and this also equal to 1 2. Okay, and t of 0 negative 1, which equal to a, b, c, d times 0 negative 1, which equal to 3 2. Okay, so that's something we can think of. And then when you multiply, you get a plus b equal to 1, c plus d equal to 2, right? So that's when you multiply out, you get that.
Professor, isn't it would be -3, -2 for that's what we solved for?
Yeah, no, this is just another way to get the matrix A.
Okay.
Yeah. All right, and for the second one, you have negative b, negative d is equal to 3 2. Okay. Okay, so this is a different approach that I just gonna think of this morning to see if we can work better for that. So because this is a matrix transformation, so we are allowed to define like this. Yes, it's a matrix transformation, so we are allowed to define by this. And we have to find a matrix A, so therefore we have, okay, let A to be A, B, C, D. And then by the definitions of that, so you have, well, when I have T of 1, 1, it would be A, B, C, D times 1, 1. And we know the result that equal to 1, 2. So similarly to the other one. So now we have 4 unknown to be solved, A, B, C, D. But then if you work on this guy, right, if you work on this guy, then you know that B is -2, and then D is -3. So you get A -2 equal to 1, and then C -3. I think I flipped it. So A -3 and then C -2 is equal to 2. Therefore, A will be 4, and then C will be 4. And therefore, you can conclude that, well, my matrix A will be 4, -3, 4, and -2. So here we also get the matrix A, which is 4, -3, 4, -2, which agree with what the method we use using the linear combinations. Yeah. So this is another approach you can use if you are asked to find matrix A. Again, I only try out with this example. I'm going to try out with furthermore. Then when we have a confirmation, I will let you know. Yeah. But I think the second approach seems to give us a much quicker answer for this problem, right? For this problem. And what happens if you don't have something similar to this, right? So we're going to try out other example. Yeah, so, we run out of time. So I'm going to stop right here. And when we come back next Monday, we will continue on this 2.6. All right, so you can go ahead and start your next homework on lyrics. Okay, so let me, all right, so let me take a snapshot real quick to see who's here, and then you can log off. All right, looking good, right? So enjoy the rest of the week, and I see you back next Monday. All right, bye for now, guys.
Good
See you,
night, Professor.
Professor.
Yeah, go on.